Hello and welcome to this video about Johnstone's triangle. This is a useful tool for thinking about chemical processes and reactions from three perspectives that can help when learning about and linking together various parts of chemistry, including bonding, rates of reaction, electrolysis and much more. Johnstone's triangle, as the name suggests, has three elements. The macroscopic, basically your observations, what you can see, feel, maybe smell. The submicroscopic or atomic. This can help you to visualize and think about how the individual atoms, molecules, or even the electrons are behaving. All of this can help build a third point of the triangle, the symbolic. This is how we communicate chemistry through things like equations, half equations, energy changes, and the like. It can also be useful for biochemistry, it's chemical processes in biology, and also for certain elements of physics, specifically for nuclear equations. Let's start with a simple process, the dissolving of sodium chloride in water. So we've got here a little animation of some salt, sodium chloride, being dissolved in water. And you can see that the person puts the salt in the water, stirs it, it goes cloudy for a little while, but then eventually the water clears up again. It becomes a colourless solution once more. At macroscopic level, what do we see? Well, we see a white crystalline solid dissolving in a colourless liquid. So we say crystalline because it's got crystals in it. It looks like sort of salt or sugar. It's not a powder, is what we mean by crystalline. The salt dissolves in the water. It appears like it disappears. It doesn't really. It's still there. It's just floating around. This must mean that NaCl, sodium chloride, is a soluble salt. At a submicroscopic level, we need to think about the structure of sodium chloride. This is, of course, an ionic compound made up of equal numbers of positive sodium ions, represented in the animation by silver positive balls, and negative chloride ions, represented by the green negative balls. The ions on the outside of each grain of sodium chloride can go into solution. That is, they separate from the rest of the grain. As they are so small, they look like they disappear. Of course, they don't really do this. They're still there. But now they're submicroscopic individual ions, effectively floating around in the water. The water has overcome the attraction between the charged ions. This sort of speaks a little bit to rates of reaction because only the particles on the outside of the grain can dissolve. So if we have a larger surface area, so smaller grains, more things can dissolve. The equation that we use for this, the third point of the triangle, is the symbolic, and this is the equation that we use to represent this. We've got NaCl brackets S, meaning it's a solid, and then the solvent we show when we dissolve in something in a solvent, we show the solvent on the arrow. Reasons for this are not really needed for GCSE, but that's H2OL, so it's a liquid, and then that produces Na plus ions, which are aqueous, so AQ, and Cl minus ions, which are also aqueous, AQ. You can see that the state symbols are vital here. They're really important because they show that we've got a solid that dissolves, and the charges on the ions are really important as well. Na plus because they're in group 1, so they lose 1 electron to produce this ionic compound, and Cl minus because they're in group 7, so they they gain 1 electron to get the full outer shell to become a negative ion. So we've used Johnstone's triangle to look at a chemical process, the dissolving of salt into water. Not a chemical reaction, but we can also apply this to chemical reactions, and that's what you're going to do now. So now it's your turn. I've put some pictures on the right hand side and an animation of what the magnesium looks like before the burn, what it looks like during the reaction, and the product that's produced. And I want you to think about the following things about the macroscopic level. What do we see? What does the magnesium look like before? Does it give you some indications as to what kind of material it is? You might know what it is already, but still we're looking for clues. What happens during the reaction? What can you see? What might you be able to feel? What might happen during the reaction? And then why do we need the Bunsen burner? So what's the point of the fire? And what does the product look like? Is energy taken in or given out? In other words, is this an endothermic reaction or an exothermic reaction? Pause the video now and have a think about those, have a discussion about those few questions. Okay, so what does the magnesium look like before? Well, it's a silver metal. We can tell it's a metal because it's ductile, it's malleable, it's strong, it conducts electricity, it conducts heat really well. It has all of the properties of a metal, and we know magnesium is a metal. It's on the right hand side of the periodic table in group 2, so we're pretty confident it's a metal. What happens during the reaction? Well, once we've lit the magnesium ribbon, it glows in incredibly bright white light. Now, this bright white light is actually quite dangerous to look at with unprotected eyes, which is why we now use eye protection for this experiment in schools. And it gives off this white smoke, and then once it's gone out, we'll have the product. Why do we use the Bunsen burner? Well, we need to overcome the activation energy for the reaction. Once we've started the reaction then produces enough heat in order to actually keep the reaction going at a decent rate. Magnesium actually tarnishes incredibly slowly, even without the fire. So we've got some magnesium in our prep room it's a few years old, and it's got little spots of magnesium oxide all over it as it's slowly starting to oxidize. But what happens in a few years, we can increase the rate of reaction so it happens in a few seconds just by increasing the temperature. The product, well, it's a white solid, a little bit of black in there as well, but the main product is white, and this is the magnesium oxide that's been produced. Is energy taken in or given out? Well, hopefully you can see it's very bright light. You can imagine if you put your hand near that, it'd be quite warm. So this is an exothermic reaction because energy is given out. Next, we're looking at the submicroscopic level. What happens? So the magnesium reacts with the oxygen in the air to form magnesium oxide. We've already established this. You need to think about what kinds of bonding does magnesium have? What kind of bonding does oxygen have? What kind of bonding does magnesium oxide have after the reaction? How many of each atom are required? So think about the groups of the periodic table that they're in. And what happens to the electrons throughout this process? Pause the video now, have a think about this, and come back when you're ready. Okay, so metallic bonding. Metals are bonded using metallic bonding. They have a bunch of ions that are in a regularly arranged lattice, and they are positive ions, so they are the nucleus and most of the electrons. A few of the electrons, the valence electrons, the outer electrons, can float around from ion to ion, temporarily filling their outer shell, or temporarily replenishing the 2 electrons for magnesium in the outer shell. These electrons can move around freely, so it conducts electricity. And if we add energy to this, if we add to heat it up, then we can break these bonds apart and the metal will melt, or it'll react with other materials. In this case, oxygen, which is diatomic, meaning that it exists as a molecule with 2 atoms of the same element bonded together covalently. And you can see the covalent bond in this case, each oxygen requires 2 additional electrons to fulfill its outer shell. So it takes those from the outer shell of it, its neighbouring oxygen. So we've got 2 oxygen atoms, each sharing 2 pairs of electrons. And then magnesium oxide, my apologies, it's behind my face. Magnesium oxide is an ionic compound. So we've got 1 of each here, metallic, covalent and ionic. Magnesium oxide's an ionic compound, so electrons from the metal will go to the oxygen, and in this case magnesium's in group 2, so it needs to lose 2 electrons. Oxygen's in group 6, so it needs to gain 2 electrons. So those 2 electrons just transfer from 1 magnesium to 1 oxygen. So if you think about that, how many atoms of each are required? Well, it's a 1-to-1 ratio, because we don't need any additional electrons from anywhere or any additional spaces from anywhere. And that leaves us with a magnesium 2+ ion and a oxygen 2- ion. Remember, Lipschitz, loss is positive, gain is negative. So magnesium's lost 2 electrons, so it becomes positive +2. Oxygen's gained electrons, so it becomes negative -2. The electrons move from the metallic sea of electrons and the covalent shared electrons, and everything's split up as we add the energy, and then it comes back together and releases energy in the ionic form. So, what's the equation that represents magnesium reacting with oxygen to make magnesium oxide? Write your answer down now, and if you can, add the state symbols and balance the equation, and then carry on when you are ready. Basically, this is the reaction. Mg plus O2 makes MgO. Remember I said oxygen's diatomic? That means it comes in pairs, so O2. Magnesium, well, we can have one magnesium atom or a million magnesium atoms. It makes no difference. So we can write that just as an Mg. And then MgO, it's a one-to-one relationship. So for every magnesium, there is an oxygen in magnesium oxide. We need to add state symbols to this, and we need to balance it. So if you've managed to balance it, then great. This is the balanced equation. 2Mg plus O2 goes to 2MgO. So that means 2 atoms of magnesium react with 2 atoms of oxygen that previously were bonded together to make 2 lots of magnesium oxide. We can then add the state symbols. We've got a solid and a gas producing a solid. Hopefully that's helped. Johnston's triangle is really, really important and really, really useful for both learning about chemistry and revising chemistry. And I want you to try applying it to some other chemical reactions, and I'll see you in another video. Thank you.